Have you ever looked up at the night sky and felt the pull of distant stars, wondering if someday we might walk among them, journey beyond our galaxy, and touch the edge of the universe itself? It is a dream woven into every science fiction story, every space fantasy, every childhood wish upon a shooting star. We imagine starships crossing the cosmic void, explorers planting flags on worlds in distant galaxies, humanity spreading endlessly across the infinite darkness. But tonight, I want to share something with you that might change how you see our place in the cosmos. The truth is, despite everything we hope for, despite all our technology and ambition, we will never leave the Milky Way. This is not pessimism. This is physics. The universe has built invisible walls around us, barriers woven from the fabric of space and time itself. These boundaries are not made of stone or steel, they are made of distance, so vast our minds cannot truly grasp it, of cosmic expansion that tears galaxies apart faster than we could ever hope to chase them, of fundamental laws that cannot be broken no matter how advanced we become. Understanding why we will never leave the Milky Way is perhaps one of the most profound realizations our species will ever face. But here is what makes this beautiful. Our galaxy holds 400 billion stars, 400 billion chances for wonder, for life, for meaning. We are not trapped in a cage, we are cradled in abundance. The Milky Way is our home, our destiny, and perhaps our paradise. If this cosmic journey sounds like something you would enjoy, take a moment to subscribe and leave a like. It helps others find these stories too. And now, let the stars guide you deeper into the night. Welcome to Sleepy Science Stories. To understand why we are confined to the Milky Way, we first need to grasp the mind-breaking distances involved. Our nearest major galactic neighbour, Andromeda, lies 2.5 million light-years away. That number is so vast it loses all meaning. So let us break it down. Light, the fastest thing in the universe, takes 2.5 million years to travel from Andromeda to us. The light you see from Andromeda tonight left that galaxy when our ancestors were just beginning to use stone tools. Imagine standing on a beach, looking out at the ocean. Now imagine that every grain of sand on that beach represents 1 kilometre. You would need more than 25,000 beaches, each covered in sand, to represent the distance to Andromeda, and that is just our nearest neighbour. The scale is so enormous that our minds cannot truly comprehend it. We can say the numbers, we can write them down, but we cannot feel them in any meaningful way. Let us try another comparison. If you could travel at the speed of a commercial airliner, about 900 kilometers per hour, it would take you over 300 billion years to reach Andromeda. That is more than 20 times the current age of the entire universe. The journey would outlast stars, outlast galaxies, outlast perhaps even the cosmos itself. And remember, Andromeda is close by cosmic standards. Here is another way to understand this distance. If you started walking toward Andromeda at the moment the first fish crawled onto land, 400 million years ago, taking one step every second without rest, you would still be in our solar system. You would not even have left the sun's gravitational influence. The Oort cloud, the outer boundary of the sun's domain, extends about 1 light-year from the sunday. Walking there would take hundreds of millions of years. Andromeda lies 2.5 million times farther. The human brain evolved to understand distances relevant to survival. We can judge whether a predator is close enough to threaten us. We can estimate how far away water might be. We can plan journeys across landscapes. But cosmic distances exist in a realm so far beyond our intuitive understanding that we struggle to make them meaningful. Numbers become abstract, divorced from experience. 2.5 million light-years is not a distance in any human sense. It is a number that represents the impossible. But distance is only the first challenge. The universe is not static. It is expanding, and that expansion is accelerating. Right now, Andromeda is actually moving toward us. The two galaxies will collide in about 4.5 billion years. But every other major galaxy is racing away from us. And the farther away they are, the faster they are receding. Most galaxies are already moving away faster than we could ever hope to catch them. This expansion is not like objects moving through space. It is space itself growing larger. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they are traveling across the rubber, but because the rubber itself is stretching. This is what is happening to the universe. Space itself is expanding, carrying galaxies with it. The discovery of cosmic expansion changed everything we thought we knew about the universe. In the 1920s, Edwin Hubble observed that distant galaxies showed redshift in their light spectra. This redshift indicated they were moving away from us. More distant galaxies showed greater redshift, meaning they were receding faster. This relationship, now called Hubble's law, revealed that the universe was not eternal and unchanging as everyone had believed. It was dynamic, growing, evolving. But the story gets stranger. In the late 1990s, astronomers studying distant supernovae made a shocking discovery. They expected to find that the universe's expansion was slowing down due to gravity. Instead, they found the opposite. The expansion was speeding up. Something was pushing galaxies apart with ever-increasing force. They called this mysterious force dark energy, though we still do not understand what it is. Dark energy is one of the deepest mysteries in modern physics. It makes up roughly 68% of all the energy in the universe, yet we do not know what it is, where it comes from, or why it exists. It does not interact with light. It does not clump like matter. It seems to be a property of empty space itself, filling every cubic centimeter uniformly. And its effect is devastating to any dreams of cosmic exploration. It is actively pushing the universe apart, accelerating the separation between galaxies at an ever-increasing rate. Think about what this means for the future. Right now, we can observe galaxies billions of light years away. Their light, though ancient, still reaches us. But dark energy is winning the cosmic tug-of-war. In the far future, fewer and fewer galaxies will be observable. Eventually, only our local group will remain visible. Every other galaxy will have receded beyond the cosmic horizon, their light redshifted into invisibility. Future civilizations will live in a much lonelier universe than we do today. Let us put this in perspective with real numbers from actual observations. The Hubble Space Telescope, and more recently the James Webb Space Telescope, have shown us galaxies over 13 billion light-years away. But here is the remarkable part. Due to the universe's expansion, those galaxies are now over 30 billion light-years from us. They are moving away at speeds greater than light itself. Yes, you heard that right. Space itself can expand faster than light, carrying galaxies with it. This does not violate Einstein's theory that nothing can travel faster than light. Objects cannot move through space faster than light. But space itself has no such restriction. Space can expand at any rate. When space expands fast enough, it carries distant galaxies away from us, faster than light can travel through that expanding space. This means that light from those galaxies, even though it has been traveling toward us for billions of years, may never reach us. The finish line keeps moving away faster than the light can run. Think of it like a treadmill. Imagine an ant trying to walk forward on a treadmill that is moving backward. If the treadmill moves slowly, the ant makes progress. But if the treadmill speeds up beyond the ant's walking speed, the ant moves backward despite walking forward. Light from distant galaxies faces the same problem. The space between us and them expands faster than light can cross it. The Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken, has mapped millions of galaxies. It has confirmed this cosmic expansion. Every galaxy beyond our local group, the small collection of galaxies gravitationally bound to the Milky Way, is destined to disappear beyond our cosmic horizon. In about 100 billion years, any civilization in the Milky Way will look out and see only darkness beyond our local group. This local group is our cosmic neighborhood. It includes the Milky Way, Andromeda, the Triangulum Galaxy, and about 80 smaller dwarf galaxies. These galaxies are gravitationally bound together. They orbit each other in a slow cosmic dance that will eventually end in merger. But everything outside this group is lost to us forever, carried away by the expansion of space. Future astronomers, billions of years from now, will face a strange situation. They will look out at the universe and see only their local group of galaxies surrounded by darkness. If they have no historical records, no data from our era, they might conclude that their galaxy cluster is the entire universe. They will not be able to see the cosmic microwave background radiation that tells us about the Big Bang. They will not be able to observe distant galaxies to discover that the universe is expanding. Much of cosmology will become impossible. We live in a privileged time. We can see the distant universe, observe the cosmic microwave background, measure the expansion rate, discover dark energy. Future civilizations will not have this opportunity. The universe is revealing its secrets to us now, but it will hide them again in the deep future. This makes our cosmic observations not just scientific curiosity, but historical records of cosmic importance. But let us say we are optimistic. Let us imagine we could somehow build a spacecraft capable of traveling at 99% the speed of light. That is far beyond anything our current physics suggests is practical. Even at this incredible speed, a journey to Andromeda would take over 2.5 million years from Earth's perspective. Due to time dilation, the travelers would experience a shorter journey, perhaps 40,000 years. But that is still longer than all of recorded human history. And Andromeda is the easy target. It is the closest major galaxy, and it is moving toward us. Every other galaxy presents an even more impossible challenge. The Triangulum Galaxy, the third largest in our local group, is 3 million light-years away. The nearest large galaxy cluster, the Virgo cluster, is over 50 million light-years distant. At 99% light speed, that is a 50 million year journey from Earth's perspective. To put this in perspective, 50 million years ago on Earth, the first primates were just beginning to evolve. Humans did not exist. The continents were in different positions. The climate was completely different. 50 million years is enough time for entire new species to evolve, for mountains to rise and erode away, for oceans to open and close. A journey taking 50 million years is not a journey in any meaningful human sense. It is geological time. It is evolutionary time. Consider also what would happen to Earth during such a journey. Would humanity even still exist when the travelers returned? Would our civilization survive? Would the planet be habitable? In 50 million years, the sun will have grown slightly brighter, changing Earth's climate. Continental drift will have rearranged the geography. Evolution will have transformed life. The humans who launched the mission would return to find a world as alien as any other planet. The energy requirements for such journeys are staggering. According to Einstein's special relativity, as confirmed by countless particle accelerator experiments at CERN and Fermilab, accelerating mass to near light speed requires exponentially increasing energy. To accelerate a single kilogram to 99% light speed requires energy equivalent to the entire power output of the United States for several years. For a realistic spacecraft weighing thousands of tons, you would need energy equivalent to converting entire planets to pure energy. Let us examine these energy requirements more carefully. Einstein's equation tells us that kinetic energy increases dramatically as velocity approaches light speed. At 10% of light speed, a 1-ton spacecraft has kinetic energy equivalent to about 100 Hiroshima bombs. That is already an enormous amount of energy, far beyond our current rocket technology. At 50% light speed, the energy requirement jumps to about 6,000 Hiroshima bombs. At 90% light speed, we need about 50,000. And at 99% light speed, the energy requirement becomes astronomical. Where would this energy come from? Our best current rocket fuel, hydrogen and oxygen, has an energy density far too low. Nuclear fission, splitting uranium atoms, is better, but still insufficient. Nuclear fusion, combining hydrogen atoms like the Sun does, is more promising, but still falls short. The only source with enough energy density is matter, antimatter, annihilation, converting mass directly into energy with 100% efficiency, according to Einstein's famous equation. But as we will see, antimatter brings its own insurmountable problems. Current spacecraft operate on energy budgets that seem laughable in comparison. The Voyager probes, powered by radioactive plutonium, generate about 400 watts of electricity. That is less than a typical home computer. The International Space Station's solar panels generate about 100 kilowatts. A nuclear power plant generates about 1 gigawatt. To accelerate even a small spacecraft to near light speed would require power output measured in terawatts or petawatts, thousands or millions of times more than the entire power consumption of human civilization. Recent studies by NASA's Breakthrough Propulsion Physics program and ongoing research at institutions like the Tau Zero Foundation have explored every conceivable method of interstellar propulsion, from fusion rockets to antimatter engines, from solar sails to theoretical warp drives. Every analysis comes to the same sobering conclusion. Even reaching nearby stars within our own galaxy pushes the absolute limits of what physics allows. Intergalactic travel is exponentially more difficult. The Breakthrough Starshot initiative, backed by Stephen Hawking and others before his death, proposes sending tiny gram-scale probes to nearby stars using powerful laser arrays. These ultralight probes would be accelerated to 20% of light speed by gigawatts of laser power. Even this modest goal faces enormous challenges. The lasers must remain perfectly focused over millions of kilometers. The probes must survive collisions with interstellar dust at relativistic speeds. And this is just to reach stars within our galaxy, not other galaxies. The laser power needed would illuminate the entire solar system, visible to any observers light years away. Some proposals involve nuclear pulse propulsion, essentially riding the shock waves of atomic bombs. Project Orion, studied in the 1950s and 60s, calculated that such a craft might reach a few percent of light speed. But the energy requirements remain staggering, and the engineering challenges multiply. Each explosion must be precisely timed and shaped. The ship must withstand thousands of nuclear detonations. And even if it worked, this gets us nowhere near the speeds needed for intergalactic travel. The Voyager missions, humanity's most distant space probes, provide a reality check. Launched in 1977, Voyager 1 is now over 23 billion kilometers from Earth. It is the farthest human-made object, but at its current speed of 17 kilometers per second, it would take over 70,000 years just to reach the nearest star, Proxima Centauri. To reach Andromeda at Voyager's speed would take over 40 billion years, 3 times the current age of the universe. Voyager's journey helps us appreciate the true scale of space. After more than 45 years of travel, moving at 17 kilometers per second, Voyager has covered less than 1/500th of 1% of the distance to the nearest star. It has not even left the Sun's influence yet. The heliopause, where the solar wind meets interstellar space, was crossed only recently. Beyond that lies the Oort cloud, a sphere of icy bodies surrounding the solar system, which Voyager will take another 30,000 years to traverse. Only then will it truly be in interstellar space. And this vast distance is just the spacing between stars within our galaxy. The gap between galaxies is incomparably larger. If stars within a galaxy are like grains of sand on a beach, galaxies themselves are like beaches separated by entire oceans. The scale multiplies in ways that mock human comprehension. But speed is not the only barrier. Intergalactic space is not just empty. It is the emptiest environment in the universe. The space between galaxies contains less than 1 atom per cubic meter. That is a trillion times less dense than the air you are breathing. This cosmic void extends for millions of light years in every direction. It is an ocean of nothingness that makes the space between stars look crowded by comparison. To truly appreciate this emptiness, imagine standing in the middle of the Sahara Desert. The desert seems empty, but it is teeming with matter compared to intergalactic space. Every breath you take contains more atoms than exist in a cubic kilometer of intergalactic space. The void between galaxies makes the best vacuum we can create in laboratories look dense by comparison. This emptiness has practical consequences. A spacecraft in intergalactic space cannot count on finding anything. No asteroids to mine for resources. No comets to harvest for water. No dust to scoop up for fuel. The ship must carry everything it needs for millions of years with no possibility of resupply. Every atom must be recycled perfectly. Every system must function flawlessly. A single critical failure means certain death with no hope of rescue. But the emptiness itself is not even the worst danger. Intergalactic space is flooded with radiation. Cosmic rays, high-energy particles from distant cosmic events, permeate the void. Without a planet's magnetic field or atmosphere to provide protection, without even the slight shielding provided by interstellar gas within galaxies, a spacecraft would be bombarded constantly by this radiation. Over millions of years, the accumulated dose would be staggering. This radiation damage is insidious and cumulative. It strikes electronics, causing malfunctions and errors. It penetrates shielding, damaging DNA in any biological organisms. It creates secondary particles as it collides with the ship's hull, sometimes making the radiation problem worse rather than better. Thick shielding helps, but adds mass, which multiplies all the other challenges. And no amount of shielding eliminates the problem entirely. Some radiation always gets through. Over geological timescales, the damage becomes catastrophic. Recent observations by the Cosmic Web Imager and studies of the intergalactic medium have revealed that this space is not completely empty. There are traces of hot gas and dark matter. But these traces are so diffuse they might as well not exist for any practical purpose. A spacecraft crossing into intergalactic space would be more isolated than anything we can imagine, unable to refuel, repair, or resupply for millions of years. These traces of gas tell an interesting story. The cosmic web, revealed through computer simulations and observations, shows that matter is not randomly distributed in the universe. Galaxies lie along filaments of dark matter and gas, like beads on strings. Between these filaments are vast voids, regions even emptier than typical intergalactic space. The universe has structure on the largest scales, with matter concentrated in some regions and absent from others. This structure formed over billions of years as gravity amplified tiny density variations present in the early universe. The cosmic microwave background radiation shows us these variations as they existed 380,000 years after the Big Bang. Over billions of years, gravity pulled matter into increasingly dense concentrations, forming the cosmic web we see today. Understanding this structure helps us appreciate that the universe is not just expanding, but evolving, changing over time. The psychological and biological challenges are equally daunting. Humans evolved on Earth, adapted to its specific conditions. We require constant supplies of food, water, and air. We need protection from radiation, stable temperatures, and gravity for our health. Creating a self-sustaining environment that could last millions of years is beyond our current technology. It is possibly beyond what is physically achievable. Our biology is intimately tied to Earth. We evolved in Earth's gravitational field. Our bones and muscles are calibrated for one gravity. Our cardiovascular system expects to pump blood against one gravity. Astronauts on the International Space Station lose bone density and muscle mass despite rigorous exercise programs. They also experience vision problems as fluids shift in their bodies without gravity to pull them down. These are not minor inconveniences. They are fundamental limitations of our physiology. We evolved breathing air at sea level pressure with 21% oxygen and 78% nitrogen. This specific mixture supports combustion at just the right rate, balances oxygen toxicity against suffocation, provides the right pressure for our lungs. Deviate too far and humans suffer. Too much oxygen causes poisoning. Too little causes hypoxia. The wrong pressure causes the bends or barotrauma. Our biology demands narrow environmental parameters. Consider also circadian rhythms. Humans evolved on a planet with a 24-hour day-night cycle. Our sleep patterns, hormone production, metabolism, and mental health all depend on this cycle. Disruption causes serious health problems. Shift workers suffer higher rates of disease. Seasonal affective disorder results from inadequate light exposure. How would humans adapt to an endless journey through space with no natural day-night cycle, no seasons, no connection to Earth's rhythms? Consider what we have learned from space stations like Mir, the International Space Station, and China's Tiangong. Despite our best efforts, these closed systems require constant resupply from Earth. They suffer from equipment failures, air leaks, and degradation over mere decades. Scaling this up to a million-year journey introduces problems we do not even know how to begin solving. The International Space Station provides valuable lessons. Despite being humanity's most advanced closed ecosystem, it requires regular resupply missions carrying food, water, air, spare parts, and equipment. Every 6 months, astronauts must perform spacewalks to repair and maintain external systems. Internal systems break down regularly. Air scrubbers fail. Water recyclers malfunction. Computer systems need updating. And this is with constant support from Earth, just 400 kilometers away. Biosphere 2, an experimental closed ecological system in Arizona, demonstrated the challenges of maintaining isolated environments. Despite careful planning and 2 years of preparation, the experiment faced numerous problems. Oxygen levels dropped unexpectedly. Carbon dioxide accumulated. Some species thrived while others died off. The system proved far more complex and unpredictable than expected. And this was on Earth, with access to emergency supplies and expert help nearby. Extrapolating to a generation ship crossing intergalactic space reveals the challenge. Every system must work perfectly for millions of years. No resupply is possible. No help can arrive. Any critical failure is fatal. The ship must be not just self-sustaining, but self-repairing, self-improving, capable of responding to unexpected problems that arise over timescales longer than human civilization has existed. The fundamental laws of physics themselves conspire to keep us trapped within our galaxy. It is not just that intergalactic travel is difficult, it is that the universe seems specifically designed to prevent it. Every breakthrough in physics over the past century, from Einstein's relativity to quantum mechanics, has only reinforced these cosmic barriers. Let us explore how the very fabric of reality builds walls we cannot cross. Special relativity, confirmed by thousands of experiments since 1905, sets the ultimate speed limit. Nothing with mass can reach the speed of light. The Large Hadron Collider routinely accelerates protons to 99.99999% light speed, requiring the energy consumption of a small city. Yet those final decimal places toward true light speed would require infinite energy. Not just in practical amounts, but literally infinite. The equation is merciless. As velocity approaches light speed, mass effectively increases toward infinity. Einstein discovered this relationship through pure thought experiments, imagining what the universe would look like moving at different speeds. His conclusion seemed absurd at first. Time slows down for moving objects. Space contracts. Mass increases. Nothing can reach light speed. But experiment after experiment has confirmed his predictions. GPS satellites must account for relativistic time dilation, or their navigation would quickly become inaccurate. Particle accelerators observe mass increase exactly as Einstein predicted. Reality obeys these strange rules, whether we like it or not. The mathematics is beautiful and brutal. The Lorentz factor, which describes how time, space, and mass change with velocity, approaches infinity as velocity approaches light speed. This infinity is not just a big number, it represents a genuine physical impossibility. To accelerate a massive object to light speed requires infinite energy. The universe does not have infinite energy. Therefore, massive objects cannot reach light speed. The logic is inescapable. The equation itself is elegantly simple. The Lorentz factor equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. At low speeds, this factor is barely different from 1. At half light speed, it is about 1.15. At 90% light speed, it jumps to 2.3. At 99%, it reaches 7. At 99.9%, 22. Each additional 9 in the decimal places causes the factor to grow explosively. At true light speed, the denominator becomes 0, making the factor infinite. Mathematics itself forbids reaching light speed. This is not a practical limitation that advanced technology might overcome. It is a fundamental feature of space-time geometry. The universe is structured in such a way that massive particles simply cannot reach light speed, regardless of how much energy we apply. we are not facing an engineering problem. We are confronting the architecture of reality itself. This is not just theoretical. We observe it every day in particle accelerators worldwide. The Stanford Linear Accelerator, Fermilab's Tevatron, and CERN's Large Hadron Collider all confirm that no amount of energy can push massive particles to light speed. If we cannot get a single proton to light speed with the most powerful machines ever built, how could we accelerate an entire spacecraft? Particle physicists have accumulated decades of data on this limitation. When accelerating particles, they observe that as energy increases, velocity increases less and less. The relationship is not linear. It takes exponentially more energy to gain each additional fraction of light speed. At 90% light speed, the particle has certain energy. To reach 99% requires more than 7 times as much energy. To reach 99.9% requires more than 22 times the original energy. Each additional 9 in the decimal places multiplies the energy requirement by more than 3. Physicists can calculate exactly how much energy would be needed to accelerate any mass to any speed below light. The numbers for spacecraft are staggering. A 1-ton spacecraft at 99% light speed has kinetic energy equivalent to about 20,000 Hiroshima bombs. At 99.9%, that increases to about 60,000 bombs. At 99.99%, nearly 200,000 bombs. And we never reach 100%. Never. Some propose antimatter propulsion. When matter and antimatter meet, they annihilate completely, converting 100% of their mass to energy according to Einstein's famous equation. This is the most efficient energy source theoretically possible, but the challenges are overwhelming. First, we must manufacture antimatter. Currently, CERN produces about 1 billion antiprotons per minute. That sounds like a lot until you realize it would take 100 million years to produce just 1 gram of antimatter. And that single gram costs about $62.5 trillion at current production rates. The production process itself reveals the fundamental problem. Creating antimatter requires enormous energy. We must accelerate particles to high speeds and smash them together, creating particle-antiparticle pairs. But this process is inefficient. Only a tiny fraction of the input energy becomes antimatter mass. The rest becomes waste heat. We essentially convert vast amounts of energy into a tiny amount of antimatter, then hope to get that energy back when we use it. The entire process operates at a net energy loss. Even if we somehow scaled up production by factors of millions, the costs remain prohibitive. Building enough antimatter production facilities would require resources exceeding the entire global economy many times over. Operating them would consume more energy than human civilization currently produces. And all this would be just to produce fuel for a single interstellar spacecraft, not an intergalactic one. Even if we solved the production problem, we face storage challenges. Antimatter annihilates on contact with normal matter. We must contain it using magnetic fields in perfect vacuum. The largest amount ever stored is a few hundred atoms, held for just 16 minutes. Storing the kilograms needed for interstellar travel requires technology far beyond our current capabilities. And the energy calculations remain daunting. To accelerate a modest spacecraft to even 10% light speed using antimatter propulsion would require fuel mass comparable to the spacecraft itself. The storage challenge is more than just technical difficulty. It is a fundamental physics problem. Magnetic fields can trap charged antimatter particles like antiprotons. but many proposed antimatter fuels involve neutral atoms like antihydrogen. These cannot be trapped magnetically. They must be held in physical traps using combinations of electric and magnetic fields, levitating the particles away from the walls. Any instability, any failure, any power interruption, and the antimatter touches the container walls and annihilates, releasing energy equivalent to a nuclear bomb. Consider also the practical engineering. An antimatter spacecraft would need not just storage but also controlled release, mixing of matter and antimatter at precise rates, channeling the resulting gamma rays for thrust, shielding to protect the crew from radiation. Each of these challenges is monumental, and this is just for interstellar travel within our galaxy, not intergalactic journeys requiring millions of times more fuel. What about theoretical wormholes or warp drives? These appear in Einstein's equations as mathematical possibilities, but every analysis by serious physicists reveals they require exotic matter, substances with negative mass or negative energy density. No such matter has ever been observed or created. The quantum vacuum can produce tiny negative energy fluctuations called the Casimir effect, but the amounts are infinitesimally small, nowhere near what is needed for macroscopic wormholes. Einstein's general relativity allows many strange solutions. The mathematics is flexible enough to permit wormholes, warp drives, time machines, and other exotic structures. But mathematics permitting something does not make it physically real. Many mathematical solutions require conditions that do not exist in our universe. Negative mass, infinite density, naked singularities, all are mathematically possible, but physically unrealized. The Casimir effect demonstrates that quantum mechanics can produce negative energy densities. Place two uncharged metal plates very close together in vacuum. Quantum fluctuations between the plates become restricted, creating slight negative energy density that pushes the plates together. This is real, measured, verified, but the effect is incredibly weak. The force on square centimeter plates, separated by 1 micrometer, is about the weight of a single bacterium. Scaling this up to macroscopic wormholes would require surface areas larger than planets, and even then might not work. Dr. Miguel Alcubierre proposed a theoretical warp drive in 1994 that would bend space-time around a spacecraft. Recent refinements have reduced the energy requirements from Jupiter masses to merely spacecraft masses. But this still requires exotic matter we cannot produce. And even if we could build it, recent papers suggest warp drives face fatal problems. They might destroy themselves through quantum effects, or trap anything inside in a region of space-time that cannot interact with the external universe. The Alcubierre drive would create a bubble of normal space-time around the ship. Space in front of the bubble contracts, bringing the destination closer. Space behind expands, increasing the distance traveled. The ship itself never moves through space faster than light. It rides a wave of expanding and contracting space. Clever mathematics, but impossible physics. Later analysis revealed additional problems. The warp bubble might accumulate particles from the space it travels through. Upon arrival, releasing the bubble could release these particles as a devastating radiation burst, destroying anything at the destination. The bubble might also be unstable, collapsing catastrophically. And most critically, the interior of the bubble might be causally disconnected from the exterior. A passenger inside might be unable to control, stop, or even detect their destination. Quantum mechanics adds another layer of impossibility. The Heisenberg uncertainty principle, confirmed in countless experiments, places fundamental limits on what we can know and control at small scales. This uncertainty prevents the perfect engineering that long-duration space travel requires. Over millions of years, quantum effects accumulate. Perfect computer memory becomes impossible. DNA degrades despite any shielding. The universe itself erodes structures through quantum tunneling. The uncertainty principle states that certain pairs of properties cannot be simultaneously known with perfect precision, position and momentum, energy and time. The more precisely we know one, the less precisely we can know the other. This is not a measurement limitation. It is a fundamental feature of reality. Particles do not have definite positions and momentum simultaneously. They exist in fuzzy quantum states. For everyday objects, quantum uncertainty is negligible, but over millions of years, tiny quantum effects accumulate. A computer bit stored perfectly today will eventually flip due to quantum tunneling. The probability is tiny in any given second, but given enough time, it becomes certainty. This places fundamental limits on information storage. Even the most perfect memory will eventually degrade. No amount of error correction can prevent this forever. DNA faces the same problem. Quantum effects can cause spontaneous mutations. Background radiation adds to this. Cosmic rays strike molecules, breaking bonds, scrambling genetic information. Shielding helps, but cannot eliminate the problem. Over millions of years, every organism aboard a generation ship would accumulate mutations. Some might be harmless, others would be lethal. The genome would drift, evolution would occur, and the species that arrives would differ from the species that departed. Consider also the arrow of time and entropy. The second law of thermodynamics, perhaps the most ironclad law in all of physics, states that entropy always increases in closed systems. A generation ship traveling for millions of years is, for all practical purposes, a closed system. Over such timescales, every mechanical system will degrade, every computer will fail. Every biological system will suffer genetic drift and mutation. We can slow these processes, but thermodynamics ensures we cannot stop them. Entropy is often misunderstood as disorder, but it is more precisely about information and possibility. High entropy means many possible arrangements look similar. Low entropy means only specific arrangements work. A functioning spacecraft is low entropy. Every part must be in the right place, performing the right function. But the universe tends toward high entropy. Parts wear out, break down, distribute randomly. Fighting this tendency requires constant energy input, constant maintenance, constant vigilance. A spacecraft is like a sandcastle on a beach. Building it requires effort and energy, creating a low entropy structure. But waves and wind gradually erode it, returning it to high entropy uniformity with the surrounding beach. Maintaining the sandcastle requires constant work. Similarly, maintaining a spacecraft requires constant energy and effort. Stop maintaining it, and thermodynamics takes over, gradually degrading every system until nothing functions. Over thousands of years, we might maintain this battle, but over millions of years, the challenge becomes increasingly impossible. Every material weakens from stress and radiation. Every seal deteriorates. Every bearing wears. Every computer accumulates errors. We can replace components, but replacement parts also age. We can build redundant systems, but redundancy only delays the inevitable. Thermodynamics always wins eventually. The universe's expansion itself creates barriers. Dark energy, the mysterious force driving accelerating expansion, was discovered in 1998 by observations of distant supernovae. This discovery won the Nobel Prize in 2011. Dark energy makes up about 68% of all energy in the universe, and it is pushing galaxies apart at ever-increasing rates. The discovery of dark energy shocked cosmologists. Two teams independently studied distant Type 1, a supernovae, explosions of white dwarf stars that serve as standard candles, objects with known intrinsic brightness. By measuring their apparent brightness, astronomers can calculate distance. These measurements revealed that the universe's expansion is accelerating. Something is pushing space apart with increasing strength. We call it dark energy because we do not know what it is. It does not emit light. It does not interact with matter except through its effect on space-time. It permeates all of space uniformly. And it is winning the cosmic tug-of-war against gravity. Where gravity tries to pull matter together, dark energy pushes space apart. And dark energy is stronger. The implications are profound. There exists a cosmic horizon beyond which galaxies recede faster than light. This horizon is currently about 16 billion light-years away. Any galaxy beyond this boundary is forever inaccessible. Not just practically difficult, but fundamentally impossible to reach. The space between us and them expands faster than light can cross it. As time goes on, this horizon encompasses fewer and fewer galaxies. In the far future, only our local group will remain gravitationally bound together. Every other galaxy will have disappeared beyond the cosmic horizon, unreachable even by light. This horizon is not a physical boundary, it is a consequence of expansion. Light from beyond this distance is fighting a losing battle. It travels toward us, but space expands faster than it can cross. The light moves forward, but the finish line moves away faster. Like swimming against a current too strong to overcome, the light makes no progress despite moving at maximum speed. As the universe ages, fewer galaxies remain accessible. Galaxies we can see today will eventually cross beyond the cosmic horizon and disappear from view. Their light will become so redshifted that it fades into undetectability. Future astronomers will have access to less of the universe than we can observe. We are living in a golden age of cosmology, able to see further and observe more than any future era will allow. Recent measurements by the Planck satellite and other observatories have refined our understanding of dark energy. The more we learn, the more permanent our isolation appears. Dark energy is not decreasing. It may even be increasing. The universe is not just expanding, it is accelerating its expansion. Future civilizations will have access to fewer galaxies than we can observe today. We are living in a special time, one of the last epochs when the distant universe is even visible. Measurements suggest dark energy behaves like Einstein's cosmological constant, a property of space itself. Every cubic meter of space contains the same amount of dark energy. As space expands, creating more cubic meters, the total amount of dark energy increases. This means the expansion will continue accelerating forever. The universe will not collapse back on itself. It will expand eternally, spreading matter ever thinner across ever vaster spaces. Some models suggest dark energy might change over time. Perhaps it will weaken, allowing expansion to slow again. Or perhaps it will strengthen, eventually tearing apart galaxies, stars, even atoms, in a Big Rip scenario. We do not know. But all observations so far suggest dark energy is constant, meaning eternal acceleration is most likely. The barriers around us are not temporary, they are permanent features of reality. Perhaps advanced civilizations could send information, if not matter. But even here, physics imposes limits. The fastest possible communication is light speed. A message sent to a galaxy 10 million light-years away would take 10 million years to arrive. A reply would take another 10 million years. A single exchange of messages requires 20 million years. Any civilization attempting this would need stability and patience beyond anything humanity has demonstrated. Imagine trying to maintain a conversation across such timescales. You send a message. The people who receive it 10 million years later are not the same species that you addressed. Evolution has transformed them. Their society has changed beyond recognition. Their technology has advanced in ways you cannot imagine. They might not even understand your message, encoded in ancient formats using obsolete mathematics. They send a reply. 10 million years later, it reaches Earth, but you are long dead. Your civilization might be dust. The people who receive the reply have no memory of the original message. They might not even know it was sent. The conversation becomes meaningless, a shouting match across eons where no continuous thread of meaning can be maintained. And this assumes the message arrives at all. Over cosmic distances, signals degrade. The inverse square law ensures that a signal broadcast from Earth becomes undetectably faint after just a few hundred light years. To reach other galaxies, we would need transmitters more powerful than stars. Even then, cosmic rays and other interference would corrupt the signal. Error correction codes could help, but only by increasing the energy requirements further. The inverse square law is geometry, not technology. Broadcast a signal from a point source and it spreads as an expanding sphere. At twice the distance, the signal is spread over 4 times the area, so the intensity is 1/4. At 10 times the distance, 1/100th the intensity. At 1,000,000 times the distance, 1/1,000,000th the intensity. The dilution is unavoidable and relentless. Our most powerful radio telescopes can barely detect signals from spacecraft at the edge of our solar system. To receive a signal from another galaxy would require antennas with collection areas larger than planets. And this is just receiving. Transmitting would require power outputs rivaling stars. The engineering challenges are insurmountable, but more importantly, the physics prevents it. There is simply not enough signal strength to overcome the noise. The timescales involved mock our biology and psychology. Modern humans have existed for about 300,000 years. Recorded civilization spans about 5,000 years. The longest-lasting human institution, arguably the Catholic Church, is barely 2,000 years old. How can we build institutions that function for millions of years? How can we maintain purpose and motivation across timescales longer than our entire evolutionary history? Studies of long-term thinking, such as the Long Now Foundation's 10,000-year clock, reveal how difficult it is for humans to plan even centuries ahead. We struggle to address climate change requiring action over mere decades. How could we maintain focus for journeys lasting longer than the time that separates us from the dinosaurs? Human psychology evolved for immediate challenges. Find food today. Avoid predators now. Build shelter before the storm. Our brains reward short-term thinking. Long-term planning is difficult and unnatural. We discount future benefits dramatically. A reward today feels more real than a reward tomorrow, even if tomorrow's reward is larger. This psychological limitation would doom any intergalactic mission. The people who begin the journey will never see the destination. Neither will their children or their children's children for thousands of generations. How do you motivate people to work toward a goal they will never experience? How do you prevent them from simply abandoning the mission or altering it for their own purposes? Consider also biological evolution. Humans separated for millions of years would evolve into different species. A crew leaving Earth today would return, if they returned, to find humanity evolved into something unrecognizable. They themselves would have evolved beyond humanity during the journey. The species that launches the mission is not the species that arrives. Evolution never stops. Every generation introduces new mutations. Selection pressures shape which mutations spread. In the confined environment of a generation ship, selection pressures would be different from Earth. Perhaps intelligence becomes less important than cooperation. Perhaps physical size decreases to conserve resources. Perhaps entirely new traits emerge. Over enough time, the changes accumulate until a new species emerges. This process does not require millions of years. Microorganisms can evolve in decades. Larger organisms take longer, but still show measurable change over thousands of years. Dogs were domesticated from wolves in just 15,000 years, creating dramatic physical and behavioral differences. What would millions of years do to humans confined in a spacecraft? The travelers who arrive would be as different from us as we are from chimpanzees. This assumes we could even maintain a viable population. Population genetics reveals the dangers of small, isolated groups. Genetic drift, inbreeding, and accumulated mutations would threaten any spacefaring population. We would need populations of thousands, perhaps tens of thousands, to maintain genetic diversity over millions of years. This multiplies all the other challenges. Larger populations need more resources, more space, more energy. The ship becomes a world, and we have enough trouble maintaining our current world. Geneticists study minimum viable population sizes for various species. Small populations face multiple risks. Inbreeding causes recessive, harmful alleles to become expressed. Genetic drift randomly eliminates beneficial alleles. New mutations accumulate faster than selection can remove them. These problems compound over time. A population might seem healthy initially but gradually decline into extinction over generations. For humans, estimates suggest we need at least a few thousand individuals to maintain genetic health indefinitely, but a generation ship would need even more. The environment is controlled, artificial, with no natural selection to remove harmful mutations. Medical technology might keep people alive who would not survive in nature, allowing those mutations to spread. Deliberate genetic management would be necessary, raising ethical questions about eugenics and reproductive freedom. Some propose generation ships, where successive generations live and die during the journey. But this raises profound ethical questions. What right do we have to condemn unborn children to life in a metal cage crossing the void? They did not choose this mission. They will never see Earth or the destination. Their entire existence is transition, means to an end chosen by ancestors they never knew. Imagine being born on such a ship. You grow up knowing you will never see Earth. Every tree, every ocean, every mountain exists only in pictures and videos. You will spend your entire life in artificial rooms, breathing recycled air, eating synthetic food. Your purpose is not your own. It is to maintain systems and produce the next generation who will also serve as means rather than ends. This violates fundamental principles of human dignity. Kant argued that people must be treated as ends in themselves, never merely as means to an end. But generation ship crew members are literally means to an end, their lives subordinated to a mission they did not choose. Is this ethical? Can we justify condemning generations to servitude for a goal they do not share? Psychological studies from isolated environments, like Antarctic research stations and nuclear submarines, reveal the mental toll of confinement. Even with communication with Earth, even with the knowledge they will return home, people in these situations often develop psychological problems. How much worse for a generation ship crew who know they will never leave, never breathe fresh air, never see an open sky. over generations? How long before resentment builds? Before society fractures? Before the mission is sabotaged by those who never wanted it? Isolation studies show clear patterns. Depression increases, anxiety rises, interpersonal conflicts multiply, people develop cabin fever, seasonal affective disorder, and other stress-related conditions. And these studies involve just months or years of isolation with eventual return home guaranteed. What would decades do? What would centuries do? What would millennia do? The social structure of a generation ship would face unique challenges. How do you govern a society where everyone is born into predetermined roles? How do you maintain law and order when there is nowhere to exile criminals, no wilderness to escape into, no frontier to pioneer? How do you keep culture vibrant when there are no new influences from outside, no immigration bringing fresh ideas, no contact with other societies? Perhaps we could use suspended animation. But current cryonics technology can freeze bodies, not revive them. The ice crystals that form during freezing damage cells irreparably. Research into vitrification, which replaces water with cryoprotectant chemicals to prevent ice formation, shows promise. But it has only succeeded with tiny tissue samples, never whole organisms larger than insects. And even if we solve the technical challenges, suspended animation just delays the problems. The ship still needs maintenance, equipment still fails, and someone must remain awake to monitor and repair systems. Cryopreservation faces fundamental biological challenges. Water expands when it freezes, rupturing cell membranes and destroying tissue structure. Ice crystals form first outside cells where solute concentration is lower. This draws water out of cells, concentrating internal solutes to toxic levels. Even if ice does not form, the osmotic stress alone can kill cells. Vitrification attempts to solve this by replacing water with cryoprotectants that do not crystallize when cooled. The tissue becomes glass-like rather than frozen. This works for small samples, like embryos and egg cells. But scaling up faces problems. Cryoprotectants are toxic at the high concentrations needed. Perfusing them throughout a human body without causing damage is extremely difficult. And cooling must be extremely rapid and uniform to prevent any ice formation. Even if we could vitrify a human successfully, warming presents equal challenges. Warming must be rapid and uniform, which is much harder than cooling. Any temperature gradient during warming can cause ice formation. And once warmed, the cryoprotectants must be removed without damaging cells. No one has demonstrated this for anything larger than insects. Whole mammals remain far beyond current technology. What about digital consciousness? Perhaps we could upload human minds to computers, eliminating biological needs entirely. But consciousness remains deeply mysterious. We do not know if it is even possible to upload a mind. The human brain contains roughly 86 billion neurons, each connected to thousands of others. Simulating this would require computers far more powerful than anything currently imaginable. And even if we could upload minds, would they remain human? Without bodies, without sensory input, without the biological drives that shape our psychology, would uploaded minds think and feel as we do, or would they become something alien? Neuroscience has made tremendous progress understanding how brains work. We can map neural connections, measure activity patterns, identify regions responsible for different functions. But we are nowhere close to understanding consciousness itself. We do not know how neurons firing create subjective experience, the feeling of being someone. We do not know if consciousness is computational, emergent, quantum, or something else entirely. Even if consciousness is purely computational, uploading faces severe challenges. We would need to map every neuron, every synapse, every molecular detail that affects brain function. Current techniques can map tiny brain regions with tremendous effort. Mapping an entire human brain at sufficient resolution would generate more data than currently exists in all computers on Earth. Processing and simulating that data would require computational power millions of times greater than today's fastest supercomputers. And even if we could create a digital simulation of a brain, would it be conscious, or would it be a philosophical zombie, behaving like a person but lacking inner experience? We have no way to know. Consciousness might require biological substrates. It might emerge from quantum effects in microtubules. It might be fundamentally impossible to transfer from one substrate to another. We simply do not know. The technological optimism of the mid-20th century has given way to a more sober assessment of limits. In the 1960s, we believed we would have Mars colonies by now, that fusion power was just decades away, that anything was possible given enough time and resources. But decades of research have revealed that many challenges are not just difficult, but approach fundamental limits. Controlled fusion has been 30 years away for 70 years now. We have not returned to the moon in 5 decades. The technological progress curve is not linear, and some barriers may simply be insurmountable. We tend to extrapolate current progress rates into the future, assuming exponential growth continues indefinitely. But this is rarely true. Progress often follows S-curves, initially slow, then rapid, then leveling off as fundamental limits are approached. Computers have gotten exponentially faster for decades, but Moore's law is ending as we approach atomic scales. Energy density of batteries improves, but cannot exceed the chemical potential of atoms. Rocket efficiency improves, but cannot exceed the energy of propellants. Some limits are economic or engineering challenges. We could return to the moon, but choose not to for cost reasons. We could build better batteries with more research. These limits might be overcome, but other limits are fundamental physics. We cannot exceed light speed. We cannot create energy from nothing. We cannot violate thermodynamics. These limits are absolute and eternal. No amount of innovation can bypass them. This is not pessimism, but realism. Physics is not holding back. The universe operates according to laws we did not write and cannot change. When those laws impose limits, we must accept them. Wishing for faster than light travel does not make it possible, any more than wishing makes gravity disappear. The universe does not care about our dreams. Science fiction often treats physics like suggestions, minor obstacles to be overcome with sufficient cleverness. But physics is not negotiable. Einstein's equations are not guidelines. The speed of light limit is not a challenge to be beaten. These are descriptions of reality itself, features woven into the fabric of space and time. A universe with different physics would be a different universe entirely, with different chemistry, different stars, different life, if any. We exist in this universe with these laws. We must work within them or not at all. Even if we solved every technical challenge, there is the question of why. What would we gain from intergalactic travel? Certainly not resources. By the time we have the technology to cross intergalactic space, we would have the technology to synthesize any element, to transmute matter at will. Resources are not rare in any meaningful sense, just rearranged energy and matter. We can get everything we need within our own solar system, or at most, our own galaxy. Atoms are atoms wherever they are found. Carbon from another galaxy is identical to carbon from Earth. Iron is iron. Gold is gold. The periodic table is universal. Any civilization advanced enough to consider intergalactic travel has long since mastered nanotechnology, molecular manufacturing, even atomic transmutation. At that level, resource scarcity is not a limiting factor. Energy is the only resource that matters, and stars provide that in abundance within our own galaxy. Not living space either. Our galaxy contains 400 billion stars. Even if we could only colonize 1 in a million, that is still 400,000 solar systems. At a generous average of 10 habitable worlds per system, that is 4 million new Earths. If humanity grew to fill all these worlds with a population of 10 billion each, we would have a total population of 40 quadrillion people. That is more than enough room for any conceivable future. To put this in perspective, Earth's current population is about 8 billion. If we multiplied that by 1 million, we would fill only a tiny fraction of our galaxy's potential. If we multiplied it by 1 trillion, we still would not fill the galaxy. The sheer number of potential habitable locations is staggering. We are not running out of room. We have barely begun to use the room we have. And this considers only naturally habitable worlds. An advanced civilization can build artificial habitats, O'Neill cylinders, rotating space stations providing artificial gravity through spin, Dyson swarms, clouds of solar collectors surrounding stars, computational substrates, converting matter into processing power for uploaded minds. Each star system could support populations far larger than a single planet. The galaxy's carrying capacity is essentially unlimited for any remotely plausible future. The knowledge and discovery argument also fails under scrutiny. Physics is universal. What we learn here applies everywhere. Other galaxies may have interesting variations, unusual stellar phenomena, different chemical compositions, but the laws governing them are the same. We can learn these laws by studying our own galaxy. We can observe other galaxies with telescopes, gathering light and data without the need to travel. The James Webb Space Telescope peers billions of light years into the universe, observing galaxies as they were in the early universe. We gain the knowledge without the journey. Spectroscopy allows us to analyze the composition of distant objects. Light from a galaxy passes through that galaxy's gas, which absorbs specific wavelengths. By examining which wavelengths are missing, we determine what elements are present. We can measure temperatures, densities, velocities, magnetic fields, all from light alone. Telescopes give us detailed information about galaxies billions of light years away, galaxies we could never visit, even in principle. The cosmic microwave background radiation shows us the universe as it was 380,000 years after the Big Bang. Observations of distant supernovae reveal how the universe expanded over billions of years. Gravitational wave detectors allow us to observe black hole mergers billions of light years away. We have a wealth of information about the distant universe without leaving our solar system. What more would visiting add? Perhaps the real motivation is psychological, not practical. Humans are explorers by nature. We have always sought new horizons. But exploration serves an evolutionary purpose. We explored to find food, resources, mates, better territories. These drives do not translate to intergalactic travel. The costs vastly exceed any possible benefit. A species that attempts what is impossible instead of what is achievable will fail, outcompeted by more pragmatic civilizations. Our exploratory instinct evolved in specific contexts. Moving to a new hunting ground might provide more food. Crossing mountains might reveal fertile valleys. Sailing to new continents opened new resources. These explorations had practical benefits that outweighed risks and costs. But intergalactic travel has no such benefits. The cost is astronomical, the timeline incomprehensible, the destination unreachable, and the benefits nil. It satisfies an emotional urge while serving no practical purpose. Mature civilizations likely recognize this. They explore thoroughly within their cosmic neighborhood. They observe the distant universe with telescopes. They build rich, complex societies utilizing their galaxy's resources. But they do not waste effort on impossible dreams. Evolution favors efficiency, not romantic gestures. Civilizations that focus on achievable goals thrive. Those that waste resources on impossible quests perish. This brings us to the Fermi paradox. If advanced civilizations are common, where are they? One answer might be that they are all confined to their home galaxies, just as we are. The universe prevents contact, not through malice, but through sheer physics. Every civilization, no matter how advanced, hits the same walls. They learn the same lessons. They discover the same limits. Perhaps advanced civilizations look at intergalactic travel, calculate the cost-benefit analysis, and decide not to bother. The implications for the search for extraterrestrial intelligence are profound. We have been listening for radio signals from alien civilizations for decades through projects like SETI. We have found nothing. Some interpret this as evidence that we are alone. But perhaps the silence has a simpler explanation. If every civilization is confined to its home galaxy by the same physical barriers that confine us, then communication between galaxies becomes nearly impossible. Even if a civilization in Andromeda wanted to contact us, how would they do it? A radio message would take 2.5 million years to arrive. By the time we received it and sent a reply, 5 million years would have passed. Their civilization might be extinct. Their planet might be gone. The species that sent the message would have evolved into something unrecognizable. Meaningful conversation across such timescales is impossible. The speed of light limit does not just prevent travel. It prevents communication, relationship, exchange of ideas. We are not just physically isolated, we are informationally isolated. This suggests that the universe might be teeming with civilizations, each locked in their own galaxy, each facing the same realization we are now facing. The cosmos is not empty of intelligence. It is filled with islands of consciousness, separated by unbridgeable voids. We are not alone in the universe, but we might as well be. The isolation is absolute. The Fermi paradox assumes that if aliens exist, we should see evidence of them. Galaxy-spanning civilizations should be visible across the universe. But perhaps the assumption is wrong. Perhaps physics prevents galaxy-spanning, let alone universe-spanning civilizations. Perhaps every civilization is confined to one star system, or at most one galaxy, by the same barriers that confine us. This would explain the silence. We do not see alien civilizations not because they do not exist, but because they are quarantined in their home galaxies, just as we are in ours. We are all islands in an ocean of space, close enough to see each other but too far apart to ever meet. The universe is full of civilizations, each alone in their galaxy, each contemplating the same cosmic isolation. This suggests something humbling but important. We are not uniquely limited. We are not failing where others succeed. We are discovering what every civilization must discover. The universe has structure, and that structure defines possibility space. Just as evolution cannot create organisms that violate thermodynamics, civilizations cannot achieve what physics forbids. Understanding our limits is part of growing up as a species. Childhood is characterized by believing anything is possible. We dream without constraint, imagine without limit. But maturity brings recognition of reality. We learn what is possible and what is fantasy. We adjust our expectations to match reality rather than demanding reality match our expectations. This is not sad, it is wisdom. A civilization that accepts its limitations is wiser than one that fights impossibilities. Every species that develops intelligence faces this same journey. First comes the excitement of discovery. Science reveals the universe's wonders. Technology provides new capabilities. The future seems unlimited. But then come the barriers. Fundamental physics imposes limits. Resources are finite, entropy increases, and the civilization must choose between wisdom and folly. Accept reality and thrive within it, or deny reality and waste effort fighting the inevitable. But here is where the story transforms. What seems like a prison is actually a gift. Let me explain why our confinement to the Milky Way might be the best thing that could happen to humanity. The transformation in perspective comes when we stop thinking about what we cannot have and start appreciating what we do have. This is not just optimistic reframing. It is a fundamental shift in understanding what makes existence meaningful. Infinite possibility sounds appealing, but it dilutes significance. Bounded reality creates meaning. A story that goes on forever with no constraints has no structure, no arc, no point. But a story with limits, with challenges, with defined scope can have profound meaning. Our confinement gives our cosmic story structure. Consider the parallel in human life. Mortality makes life precious. If we lived forever, each moment would lose significance. We could always do something later. Nothing would be urgent or important. But knowing our time is limited makes us treasure each day. Similarly, knowing our cosmic realm is bounded makes every star system precious, every discovery important, every moment of existence meaningful. Limitation creates value. First, consider the scale: 400 billion stars. If you visited one star system every single second, it would take over 12,000 years to see them all. At a more realistic pace of exploring one system per year, it would take 400 billion years, 30 times the current age of the universe. Our galaxy is not a prison. It is an empire vaster than we could ever fully explore. Think about what 400 billion means. If every person currently alive claimed one star, most stars would still be unclaimed. If humanity expanded to 1 trillion individuals, each could have 400 stars. If we grew to 1 quadrillion, each could have multiple star systems. The scale defies comprehension. We worry about being trapped when in truth we have more space than we could use in geological timescales. Each star is unique. They vary in size, temperature, composition, age. Some are newly born, surrounded by protoplanetary disks. Others are ancient, stable for billions of years. Some are binaries, 2 stars orbiting each other. Others have planetary systems of bewildering diversity. Every star is a laboratory of physics, a source of energy, a potential home. Recent exoplanet discoveries reveal the true richness of our galactic inheritance. The Kepler mission and TESS have shown that planets are the rule, not the exception. Statistical analysis suggests our galaxy hosts over 100 billion potentially habitable worlds. Each one is a complete world with its own geography, its own weather, possibly its own biology. Each is a unique puzzle that could occupy humanity for millennia. The Kepler mission observed over 500,000 stars, finding thousands of exoplanets. From this sample, astronomers extrapolate that virtually every star has planets. Many have multiple planets. Roughly 20% of Sun-like stars have Earth-sized planets in habitable zones where liquid water could exist. The numbers are staggering. Our galaxy contains tens of billions of Earth-like worlds. But habitability is just the beginning. Every planet is unique. Different sizes, different orbits, different compositions. Some might be water worlds, entirely covered in deep oceans. Others might be desert planets with minimal water. Some might have thick atmospheres creating runaway greenhouse effects. Others might have thin atmospheres that provide little protection. The variety is endless. The diversity within our galaxy surpasses anything science fiction imagined. We have found hot Jupiters orbiting their stars in days, super-Earths with surfaces of diamond or water, rogue planets drifting between stars, planets orbiting binary stars like Tatooine. The TRAPPIST-1 system alone has 7 Earth-sized worlds. The variety within our single galaxy exceeds what most fiction places in entire universes. Consider the sheer strangeness we have already discovered. There are planets where it rains molten glass sideways in supersonic winds, worlds tidally locked to their stars, one side eternally scorched, the other frozen in perpetual night. Ocean planets where liquid water extends hundreds of kilometers deep, creating pressures that form exotic ices even in the warmth of the deep interior. Planets with multiple suns, casting complex patterns of shadows and creating seasons of bewildering complexity. We have found planets orbiting dead stars, worlds that survived their sun's explosive death and now orbit the cooling corpse. We have found planets being torn apart by their star's gravity, leaving comet-like tails of vaporized rock. We have discovered systems where planets orbit in perfect resonance, their gravitational dance maintaining stability for billions of years. Each discovery expands our understanding of what is possible, what forms planetary systems can take, what environments might exist. And we have barely begun. Most of the exoplanets we have found are large and close to their stars, simply because those are easiest to detect. Our techniques are only now becoming sensitive enough to find true Earth analogues, small rocky worlds orbiting at comfortable distances from sun-like stars. The diversity we will discover in the coming decades will make our current catalogue seem like a tiny sample of cosmic possibilities. The galaxy is full of wonders we have not yet imagined. Hot Jupiters were one of the first types of exoplanets discovered, and they surprised astronomers. These are gas giants, more massive than Jupiter, but orbiting closer to their stars than Mercury orbits the Sunday. Their years last mere days. Their surfaces are scorched by intense radiation. We do not have planets like this in our solar system. Their existence challenged theories of planet formation and migration. Super-Earths are another surprise. These are rocky planets, larger than Earth, but smaller than Neptune. Again, our solar system has no examples. Are they giant rocky worlds? Or do they have thick hydrogen atmospheres making them mini-Neptunes? We do not know. Studying them will reveal new types of planets we never imagined. Water worlds might exist, planets with so much water that it covers the entire surface, hundreds of kilometers deep. At the bottom of such oceans, pressure would create exotic forms of ice despite the heat. Life in such worlds would be entirely aquatic, evolving in darkness at deep vents. What forms might it take? What intelligence might arise from purely oceanic evolution? Diamond planets might exist around carbon-rich stars. Instead of silicate rocks, their mantles could be solid diamond. Mountains of diamond, oceans of liquid carbon. The physics would be familiar, but the chemistry entirely alien. Such worlds would glitter like jewels in the darkness, treasures beyond measure that we could never claim. Being confined to the Milky Way grounds us in reality rather than fantasy. Instead of dreaming impossible dreams of intergalactic empire, we can focus on achievable goals. Interstellar travel within our galaxy, while extremely difficult, is not impossible. Generation ships, suspended animation, or life extension could make journeys to nearby stars feasible. We can realistically dream of humanity spreading across our galaxy over millions of years, Realistic interstellar travel might look very different from science fiction. No warp drives or hyperspace. Instead, slow, patient journeys, taking thousands or tens of thousands of years. Ships would be cities, complete ecosystems, providing everything needed for multiple generations. Or perhaps ships would carry frozen embryos and artificial wombs, with AI systems raising the first generation upon arrival. Life extension might make personal interstellar travel possible. If humans could live thousands of years, individual people might experience journeys to nearby stars. Medical nanotechnology, genetic engineering, uploading to artificial bodies, any of these might extend human lifespan enough to make interstellar travel personally meaningful rather than a relay race across generations. Our isolation makes us cosmically precious. If life is rare, and intelligence rarer still, then Earth might harbour the only conscious observers in the Milky Way. We are not just one civilization among countless others. We might be the only witnesses to our galaxy's beauty. Every sunset, every scientific discovery, every moment of wonder might be unique in our cosmic neighborhood. This is a profound thought. The Milky Way has existed for over 13 billion years. It has churned through countless stellar generations, creating heavy elements, forming planetary systems, and yet it might have produced consciousness only once. On this small blue world orbiting an average yellow star, matter has arranged itself into forms that can contemplate existence itself. We are the universe becoming aware of itself. If we are alone, then our significance multiplies. We are not witnesses among many, but the sole witness. Every work of art, every scientific theory, every moment of love or joy or understanding is unique. The Milky Way has created consciousness, and we are it. Our existence transforms the galaxy from mere matter to something capable of meaning. This uniqueness brings responsibility. We are not just living for ourselves, but as representatives of what is possible in our galaxy. If we destroy ourselves through war, environmental collapse, or accident, we might be extinguishing the only consciousness the Milky Way has ever produced. Our survival becomes a cosmic imperative, not just a selfish desire. The universe is mostly matter without consciousness. Stars burn unobserved, galaxies collide unwatched. Planets form and erode without anyone to notice or care. This was the state of the Milky Way for nearly its entire history. But now there is consciousness here. We transform the galaxy's story from mere physics to narrative. Events that occur now occur before witnesses. The galaxy has become conscious of itself through us. If we vanish, consciousness might vanish with us. The galaxy would return to mere mechanism, beautiful but meaningless. Stars would continue burning, but there would be no one to appreciate their light. Planets would continue orbiting, but there would be no one to study their motion. The universe would continue its expansion, but there would be no one to discover its secrets. This responsibility is the price of consciousness. The finite scope of our galaxy makes complete understanding possible. Unlike the infinite universe, our galaxy is comprehensible. Future humanity could realistically catalogue every star, map every planet, understand every phenomenon within the Milky Way. We could achieve complete knowledge of our cosmic home. That is something impossible if we could spread across infinite galaxies. The universe might be infinite, we do not know, but infinity brings its own problems. An infinite universe cannot be fully explored, fully understood, fully catalogued. There is always more. No matter how much you discover, infinity remains. But a galaxy is finite. 400 billion stars, a specific number, countable, understandable. We can imagine completing the task of understanding our galaxy, even if it takes billions of years. This completeness brings meaning. Infinite tasks are meaningless because they can never be finished, but finite tasks, however large, can be accomplished. Future humanity might one day say, "We have visited every star, studied every planet, understood every mystery of our galaxy." Such completeness is impossible with an infinite universe, but achievable with our finite cosmic home. Being trapped together might save us from ourselves. If we could escape to other galaxies, humanity might fragment irreversibly. Different branches of humanity would evolve in isolation, becoming alien to each other. But confined to one galaxy, we are forced to eventually reconcile, cooperate, and unite. Our shared imprisonment might be what finally brings humanity together as one species with one destiny. History shows how isolation breeds divergence. Humans spread across Earth, and different populations develop different languages, cultures, physical characteristics. The process took mere thousands of years. Given millions of years of complete isolation in different galaxies, human branches would become separate species, unable to interbreed, unable to communicate, unable to recognize each other as kin. But confined to one galaxy, we remain in contact. Light-speed communication limits delay, but does not prevent it entirely. A message sent across the galaxy takes 100,000 years, but it arrives. Slow communication is still communication. It maintains a thread of connection, however tenuous. We remain one civilization, one story, one species. The Milky Way's collision with Andromeda in 4.5 billion years is not a catastrophe but an opportunity. Our local group will merge into one giant galaxy, doubling our realm. Individual solar systems will rarely collide. The merger will trigger new star formation, creating fresh worlds for our descendants. Our kingdom will expand, giving future humanity even more to explore. Galaxy collisions sound violent, but they are gentle on small scales. Galaxies are mostly empty space. The stars in the Milky Way and Andromeda will pass through each other like two clouds merging. Individual star collisions are extremely unlikely. The Sun will not hit another star. Earth will not be destroyed. We might not even notice the collision from Earth's surface. But the merger will reshape both galaxies. Gravity will pull stars into new orbits. The Milky Way's spiral arms will distort. Andromeda's structure will change. Eventually, the two galaxies will settle into a new form, probably an elliptical galaxy rather than spirals. This new galaxy, sometimes called Milkomeda or Milkdromeda, will be our future home. The merger will trigger new star formation. When galaxies collide, their gas clouds compress. Compressed gas collapses, forming new stars. We will witness a cosmic fireworks display, a burst of star formation that might last millions of years. New stars mean new planetary systems, new worlds for future humanity to explore. Our realm doubles just when we might be running out of new places to visit in our original galaxy. Understanding our limits liberates us from impossible expectations. We are not failing to build an intergalactic civilization. We are succeeding at what is actually possible. Every probe we send to another star, every world we terraform, every colony we establish, is a victory against the vast distances and harsh physics that constrain us. Humanity has a history of transforming impossibilities into achievements. We learned to fly despite being earthbound primates. We walked on the moon despite having no natural space adaptations. We split the atom despite its seeming indivisibility. These victories came from recognizing limits and working within them, not from denying reality. We will not travel between galaxies, but we can travel between stars. That is still amazing, that is still worthy of our efforts. Establishing even a single colony at Alpha Centauri would be an achievement rivaling anything in human history. And we have billions of stars to potentially visit. We have work for billions of years. That is success, not failure. Our cosmic isolation makes every discovery within our galaxy more precious. When we find life on Europa or Enceladus, when we decode signals from another civilization, when we discover new physics, these will not be routine events in a galaxy-spanning empire. They will be unique moments in our isolated pocket of consciousness. Scarcity creates value, and our isolation makes every discovery priceless. Finding life anywhere, even simple microorganisms, would be one of the most profound discoveries in history. It would answer the ancient question, are we alone? If we find even bacteria on Mars or fish in Europa's oceans, it means life is not a unique Earth phenomenon, but a cosmic one. And if life is common, intelligence might also be common. We might share the galaxy with other minds, or we might not. We might search thoroughly and find we are alone. This would also be profound. It would confirm that we are rare, precious, the only intelligence in billions of stars. This uniqueness brings both privilege and responsibility. We are the galaxy's sole witness, its only hope for meaning and purpose. Every discovery in our limited realm matters more because of our limitation. If we could explore infinite galaxies, each discovery would be diluted by infinity. There would always be more, always another. But in our finite galaxy, each discovery is one less mystery, one more piece of complete understanding. We move toward total knowledge, and each step matters. The artistic and cultural implications are profound. Confined to one galaxy, human culture will not fragment into mutually incomprehensible traditions. We will maintain enough connection to share art, literature, music, and ideas. The works we create will not be lost to impossible distances, but can enrich all of humanity across our galaxy. Culture thrives on exchange. Artists inspire artists. Writers learn from writers. Musicians build on musical traditions. This exchange creates richness, diversity, and progress. But exchange requires communication. If humanity fragments across galaxies with no communication possible, each branch develops independently. Art becomes local, not universal. Humanity's cultural heritage splits into incompatible pieces. But confined to one galaxy, we maintain cultural continuity. A song composed near the galactic center can eventually be heard on the rim, perhaps thousands of years later. A book written in one arm of the spiral can be read in another. The time delay is enormous, but it is finite. We remain one civilization, one culture, able to share and appreciate each other's creations. Future historians will study humanity's cultural evolution across the galaxy. They will trace how ideas spread from star to star, how art styles emerged and transformed, how different colonies adapted culture to their local environments while remaining part of the greater whole. Our confinement preserves this unity and makes cultural history comprehensive rather than fragmentary. Science benefits from our confinement. Instead of spreading our efforts across impossible distances, we can focus on deeply understanding our local universe. The James Webb Space Telescope, the upcoming extremely large telescopes, and future observatories can thoroughly study our galaxy and local group. Concentrated effort yields deeper understanding than scattered exploration. Science advances through accumulation. Each discovery builds on previous discoveries. Each experiment tests theories developed from earlier experiments. This process requires continuity. Scientists must communicate, share data, verify each other's work. But communication across intergalactic distances would be essentially impossible. Science would fragment into isolated efforts with no synthesis. Confined to one galaxy, we can build a unified scientific project. Observatories across the galaxy contribute data to common databases. Scientists separated by thousands of light years collaborate asynchronously, each building on the other's work. Over millions of years, we could develop a complete understanding of our galaxy's structure, history, and phenomena. Complete knowledge is possible with concentration, but impossible with diffusion. Our limitation teaches humility and wisdom. The universe has shown us our place, not as potential gods ruling countless galaxies, but as conscious matter confined to one galactic island. This humility might be what we need to survive and thrive. Hubris leads to downfall. Accepting our limits leads to wisdom. Mythology is full of cautionary tales about hubris. Icarus flew too close to the Sunday, the Tower of Babel reached for heaven. Prometheus stole fire from the gods. All these stories warn against overreaching, against attempting what is forbidden or impossible. These are not just stories, they reflect deep wisdom about knowing and accepting limits. Species that overreach waste resources on impossible goals. They neglect achievable improvements for fantasy. They make enemies of reality itself by demanding what cannot be. Such species fail, outcompeted by wiser neighbours who work within constraints rather than against them. Accepting limits is not defeat, it is strategy. Wisdom means understanding what is possible and focusing effort there. A wise civilization transforms its galaxy into a garden, filling it with life and intelligence and beauty. A foolish civilization wastes effort dreaming of other galaxies while its home falls apart. We can be wise. We can accept our cosmic island and make it wonderful. That is success far greater than futile attempts at the impossible. The search for meaning becomes clearer when we accept our boundaries. Instead of seeking purpose in impossible expansion, we find it in perfecting our corner of the universe. We can transform the Milky Way into a garden of consciousness, a beacon of life and intelligence in an otherwise empty cosmos. Purpose emerges from context and constraint. An artist given infinite canvas and infinite time produces nothing, paralyzed by limitless possibility. But give that artist a defined canvas, a deadline, specific constraints, and creativity flourishes. The limitations, focus, effort, channel, energy, make choices meaningful. Our cosmic canvas is the Milky Way. Our constraints are the laws of physics. Within these boundaries, we can create something extraordinary. Think about what it means to perfect a galaxy, not just to inhabit it, but to truly make it flourish. We could seed lifeless worlds with carefully designed ecosystems, transforming barren rocks into living planets. We could establish civilizations around every suitable star, each unique, each contributing to the greater tapestry of galactic culture. We could preserve endangered species from Earth on distant worlds, ensuring that no form of life is ever lost. We could create art on planetary scales, music that resonates across star systems, science that unravels every mystery our galaxy contains. This vision is not fantasy. It is achievable within the laws of physics, given enough time and wisdom. We have billions of years ahead of us if we survive our current challenges. The Milky Way could become something unprecedented in the universe, a galaxy that has awakened to consciousness, that knows itself, that has transformed from mere matter into meaning incarnate. This is a purpose worthy of our species, grand enough to inspire countless generations yet bounded enough to be comprehensible and achievable. Philosophers have always asked about life's meaning and purpose. In a truly infinite universe where we could expand forever, purpose becomes diluted. We are just one more civilization among infinite civilizations, our achievements duplicated infinite times elsewhere, our existence ultimately meaningless in the face of infinity. But in a bounded realm, we gain significance. We are the Milky Way's consciousness. Our purpose is clear: understand, preserve, and enhance this pocket of the universe given to us. We can envision a far future where the entire galaxy teems with life, every star system explored, understood, utilized, dead worlds terraformed into gardens, artificial habitats orbit countless stars. The galaxy becomes alive, conscious, meaningful. This is a purpose worthy of our efforts, achievable yet grand, bounded yet vast. Future technologies we develop will not be wasted on impossible intergalactic dreams, but focused on achievable goals. Fusion power, antimatter production, life extension, terraforming, artificial intelligence, all can be directed toward making our galaxy a true home for humanity and whatever intelligences we create or encounter. Technology should serve human flourishing, but technology aimed at impossible goals wastes resources that could improve actual lives. Every dollar spent researching warp drives that cannot exist is a dollar not spent solving problems that actually affect people. Every brilliant mind working on intergalactic travel fantasies is a mind not working on extending life, curing disease, or improving quality of life. Focused on realistic goals, our technology can achieve wonders. We can extend human lifespan, perhaps indefinitely. We can cure diseases. We can spread life throughout the galaxy. We can create artificial intelligences that help us understand the universe. We can build civilizations of unimaginable richness and complexity. All this is possible within our cosmic limitations. All this is sufficient for meaning and purpose. The story of humanity becomes more coherent when bounded. Instead of fragmenting across impossible distances, our narrative remains unified. Future historians will tell the story of one species in one galaxy, a complete tale with beginning, middle, and end. Our cosmic story has scope and limits, making it meaningful rather than infinite and therefore meaningless. Every good story has structure: beginning, middle, end, rising action, climax, resolution. Infinite stories lack structure. They continue forever without conclusion. But bounded stories can be complete. Humanity's story in the Milky Way has shape. We begin on Earth. We spread through the solar system. We reach the stars. We fill the galaxy. We understand our cosmic home completely. This is a story with meaning, with narrative arc, with the possibility of completion. Future humanity will look back on this era with interest. This is when we realized our limitations. This is when we abandoned fantasies and embraced reality. This is when we committed to making our galaxy the best it could be, rather than dreaming of impossible alternatives. This era matters because we chose wisdom over hubris, reality over fantasy, achievement over dreams. As you look up at the night sky, do not see a prison of unreachable lights. See your inheritance, 400 billion stars that belong to you and your descendants. Every point of light in the Milky Way is a destination you or your children's children might someday reach. That is not limitation. That is abundance beyond imagination. Those points of light are real places, massive balls of nuclear fire, forging elements, radiating energy, surrounded by worlds we cannot yet see but know are there. Each one is an adventure, a mystery, a new chapter in humanity's story. We have more destinations than we could visit if every human alive became an explorer. We have more territory than we could settle if we multiplied our population 1,000,000,000,000-fold. This abundance makes our confinement absurd to lament. We worry about being trapped while standing before riches we cannot exhaust. It is like a man in a vast palace complaining he cannot visit the palace next door. First, explore every room of your own palace. You will find a lifetime of wonders. We have a cosmic palace. It will take billions of years to fully explore it. We should get started. We will never leave the Milky Way. But that is not a tragedy. It is a gift. It means we are home. It means we belong here. It means this galaxy, vast and beautiful beyond comprehension, is ours to explore, understand, and cherish. Home is not a limitation. Home is where we belong, where we fit, where we can thrive. The Milky Way is our home, shaped by the same cosmic forces that created us, operating under the same physical laws that enable our existence, filled with worlds made of the same elements that compose our bodies. We are not aliens in the Milky Way. We are natives. This is where we belong. Other galaxies are beautiful from distance, but they are not home. They operate under the same physics, contain the same types of stars and planets, but they are not ours. They belong to their own potential civilizations, if such exist. Or they remain empty, beautiful but meaningless, without consciousness to appreciate them. Either way, they are not our concern. Our concern is here, in this galaxy, our home. We are not trapped. We are embraced by spiral arms of stars that define the boundaries of our cosmic kingdom. The universe has given us exactly what we need. Not infinite space that would dilute our existence into meaninglessness, but a bounded realm, vast enough for endless discovery, yet small enough to remain coherent. Imagine being given infinite resources. You could never use them all. Their abundance makes them meaningless. But imagine being given vast but finite resources, enough for billions of years of use, but countable, manageable, appreciable. You value them, you plan their use carefully, you appreciate your fortune. This is what the Milky Way is. Not infinite meaningless void, but vast meaningful realm. The spiral arms that define our galaxy are not walls, but embrace. They are the boundaries of possibility, not impossibility. They define the scope of our story, give it shape and meaning. Within these arms we find purpose. Without them, we would be lost in infinite, meaningless space. The boundaries are a gift, not a curse. The Milky Way is our cradle and our destiny, our prison and our paradise, our limitation and our liberation. In the cradle, we were born. Earth formed in the disk of the young Milky Way, condensing from dust created in stellar furnaces over billions of years. The galaxy made us. It provided the elements of our bodies, the energy of our star, the stability for life to evolve. We arose from the galaxy as the galaxy became conscious of itself. But we should understand the profundity of this more deeply. Every atom in your body was forged in stars. The calcium in your bones was created in stellar explosions. The iron in your blood was synthesized in supernova cores. The oxygen you breathe was manufactured in stellar fusion. You are literally made of stardust, assembled from the remnants of dead stars that exploded billions of years ago. The galaxy did not just provide a home for humanity. It built us atom by atom from its own substance. This connection is not metaphorical. It is physically, chemically, biologically real. We are the galaxy's children in the most literal sense possible. The same processes that formed the spiral arms also formed us. The same physics that ignites stars also powers our metabolism. The same chemistry that creates nebulae also creates DNA. We are not separate from the Milky Way. We are part of it, expressions of it, the universe contemplating itself through forms made of its own material. Our destiny is to spread throughout this cradle, to fill it with life and consciousness, to transform it from mere matter into something meaningful. We will reach the stars, establish colonies, create civilizations, and perhaps encounter others doing the same. Over billions of years, we will make the Milky Way alive. This is our destiny. But destiny is not predetermined. It is possibility that must be actualized through choice and action. We could fail. We could destroy ourselves before reaching the stars. We could fall into stagnation, giving up on exploration. We could fragment into warring factions that waste resources on conflict instead of cooperation. Our destiny is not guaranteed. It is a potential future we must work to achieve, generation after generation, millennium after millennium, choosing wisdom over folly, cooperation over conflict, growth over stagnation. The Milky Way offers us the opportunity to become something magnificent. Whether we accept that opportunity is up to us. Prison implies unjust confinement, but there is no injustice here. Physics is not punishment. We are not imprisoned by malicious forces, but bounded by natural law. And paradoxically, this limitation liberates us. It focuses our efforts. It gives us achievable goals. It makes our story meaningful rather than diffuse. Paradise is a place of perfect beauty and happiness. The Milky Way can become this. Not naturally, but through our efforts. We can spread life to lifeless worlds. We can fill emptiness with consciousness. We can transform raw matter into art and science and love. Our limitation and our capability together create paradise from potential. So embrace our galactic confinement. Celebrate that we have 400 billion stars to explore, rather than mourning the trillions we will never reach. Find joy in the fact that we are all in this together. One species in one galaxy, sharing one cosmic destiny. Embrace limitation as liberation. Let go of impossible fantasies. Accept reality. Within acceptance comes freedom. Freedom to act effectively rather than dream uselessly. Freedom to achieve rather than fantasize. Freedom to build paradise rather than waste effort reaching for mirages. Celebrate abundance. 400 billion stars. We lament being confined while standing before riches that mock limitation. We have more than we could ever use, more than we could ever explore, more than we could ever understand. This is cause for celebration, not mourning. Find joy in community. We share this cosmic island. All humanity, perhaps all intelligence in the galaxy, shares one bounded realm. We are in this together. Our fates are linked. Our stories intertwine. This creates bonds impossible in infinite space where everyone disperses never to meet again. Our confinement creates community, and community creates meaning. The universe has given us the Milky Way, and that is more than enough for any species to find meaning, purpose, and endless wonder. We will never leave the Milky Way. And perhaps in the end, that is exactly as it should be. The universe is wise in ways we are only beginning to understand. It has given each region of space the possibility of consciousness, while preventing that consciousness from spreading everywhere. Each galaxy becomes a separate experiment, a separate story, a bounded realm where meaning can emerge. This might be the optimal structure for a meaningful universe. Not infinite uniformity, but bounded diversity. not one story, but many, each complete in itself. We will never leave the Milky Way. This truth, once accepted, transforms from tragedy to gift. It defines who we are, clarifies our purpose, focuses our efforts. We are not wanderers destined to roam forever. We are homesteaders with a vast estate to cultivate. Our story has boundaries, and those boundaries give it meaning. Accept them. Embrace them. They are not limitations, but liberation. There is profound wisdom in acceptance. Not resignation, not giving up, but clear-eyed recognition of reality, followed by determination to thrive within it. This wisdom has been hard-won through centuries of scientific discovery. Each generation has learned more about the universe's true nature, and each generation has had to adjust its dreams accordingly. We once thought the Earth was the center of everything. Then we learned we orbit the Sunday. We thought the Sun was special. Then we learned it is one of billions. We thought we could explore everywhere. Now we learn we are bounded. Each realization has made us smaller in scope, but larger in understanding. We are not the center of everything, but we are witnesses to everything. We cannot go everywhere, but we can understand everywhere through observation and theory. Our significance comes not from being physically large or central, but from being conscious, capable of understanding, able to appreciate the vast universe even if we cannot touch all of it. This is the wisdom of maturity, accepting what we are while celebrating what we can become within our limits. If you made it through this entire cosmic reality check, you are exactly who I make these videos for. Subscribe for more mind-expanding journeys through space and time. And please give a thumbs up if you enjoyed this video. I am sure you will love this other one at the left side of the screen. Time dilation, why moving faster slows you down? In this video, discover the real science behind time dilation, Einstein's special relativity, and why astronauts, GPS satellites, and even you experience time differently depending on speed and gravity. See you there.